All right, so what does this t distribution that this beer guy discovered? Um, yeah, I don't think this is really, I mean, you can read through it, but it's more of what I just had up there. So I want to show it to you what it looks like on the calculator. Now, in order to graph it, you actually graph the tPDF. One of the things we never talked about was a PDF with the normal. We never use that function, and you should never use it in APStat. But in order to graph it, I am gonna show you. So I'm gonna go norm PDF. What this function does is it actually gives you the normal curve instead of having to write down the equation. So there it is. This is a normal model that you know and love. I'm going to do a zoom box on it so it's a little. So let's go 3 standard deviations, right? It's about sensible. There we go. Okay. So this is the normal curve. So let's graph the t-distribution. Now, t-distribution has degrees of freedom. So to do that, we're going to want to insert a slider. We'll call it t. So we can change this. We'll go from 0 degrees of freedom to 50. And we'll count by ones. Okay. So what this little slider will do is it'll take different degrees of freedom. Why did I call it t? I should have called it df. Degrees of freedom. There we go. Doesn't really matter though, does it? Oh no, I can't select the element anymore. Oh well, it's alright. Good enough. So now I want to graph a new function called the tPDF. Guys, again, you'll never have to do this in class. I'm just wanting to show you what the curve looks like for different. So it's x comma, and then we have to put in the degrees of freedom. So I'll just put in df, and it should go bold because it's taking it from this. So here's the t curve. The red is the t curve. The blue is normal. So when our degrees of freedom is 1, they look quite a bit different. But it's still symmetric. It's still kind of bell-shaped and unimodal. 2 degrees of freedom, 5 degrees of freedom, 6, 7, 8, 9, 10, 20, 40, 50. So as your degrees of freedom increases, this gets closer and closer to the normal model. Because as your sample size gets bigger, if you take samples of size 50, now your S is a really good estimator for your population standard deviation. So this t curve doesn't need to be very different than the normal model, right? But it takes on a lot of different values. But in general, it's flatter in the middle, less values, or not flatter, it's shorter in the middle, so there's less area in the middle and more area on the tails. So what's going to happen whenever we need to take a 95% confidence interval on the normal curve, 1.96 gets you 95%. But on this distribution, you're not going to get 95% because there's less area in the middle. You're going to have to go further out to get the same amount of area. Further out means you have a bigger t crit than the z crit, means you have a wider interval, means you're more likely to capture that true population mean. Okay? And the degrees of freedom is 1 minus your sample size. So that's it. That's what it looks like. As the sample size increases, the t curves becomes closer and closer to normal. I do want to point out to you, though, it never is exactly the same. In fact, if I go to 50 degrees of freedom, you can't hardly tell the difference by looking at it. But if you zoom in on the top of it, there's a pretty big, if you zoom in close enough, so it's always different. Even if you went 100 degrees of freedom or 1,000 degrees of freedom, there's just a slight difference of it, okay? So working with the t-distribution. So what do you need to know how to do? Well, you need to know how to calculate areas and critical cutoffs with a t-distribution just like you do with the normal distribution. So let's do some examples. So t sub 4 means a t-distribution with 4 degrees of freedom. That's the notation. So let's find the area between +2 and -2 on the standard normal curve for z values. It's going to be about 95%. The function is normal CDF. Statistics, distributions, normal CDF. Let's go from -2 to +2. 95.45. So this is 0.9545. But if we do a t-distribution with 3 degrees of freedom, it's going to be flatter, it's going to be shorter and wider. So if you use the same cutoffs and it's shorter and wider, we're going to get less area. We're not going to get 95%. So and here's the thing is if you know how to use the normal functions, you can use the t. They're all the exact same function. So this would be the t-CDF, -2 and 2. Only with the t-curve, you always have to put in the degrees of freedom because each curve is different with different degrees of freedom. This is 3. 86.1. Okay, so now 10 degrees of freedom. Now 10 degrees of freedom is going to be more normal. Closer to normal. It's probably going to be bigger than this, but still less than that. Actually, we can just do these last two, crank them out, 10 and 50. Just change that last input to 10. 92.7. Getting closer. 50 degrees of freedom. I would think that would be pretty close because you saw the curve. It's pretty close to normal at 50 degrees of freedom. 9491.9491. Still a little bit of a difference, but really not very much at all. Okay. Between negative 1.5 and 2.3 with 10 degrees of freedom. I don't know. That's kind of a weird question, but whatever, I guess. Negative 1.5 to 2, I don't remember what it was, 2.3 with 10 degrees of freedom. 896. Okay. 0.896. Okay, good. So this is where we're going to be doing though with our confidence intervals. We're going to be calculating t-crits, cutoff values. So suppose we want 95% confidence. So just remember, if it was a z-crit with 95% confidence, it'd be 1.96. But if you want to get 95% of the area on a t-distribution with degrees of freedom equal to 4, it's going to be different. We still got 0.025 on the tails, so let's put the left tail in. Now you're going to use an inverse t, just like you would use an inverse normal. Area to the left, 0.025. Degrees of freedom, I think it was 4. 2.776. So I just want to point out to you that this is actually larger than the 99% confidence level for z-crits. Because your sample size is so small. So if you had a small sample size, this is going to really increase your margin of error. But that's the correction that's needed so that you can use S to approximate sigma. Okay? 99% confidence with 15 degrees of freedom. 99 in the middle. 1% on two tails. 0.005 on one tail. Now we have degrees of freedom equal to 15. So T15 crit. See, once you know how to do one, you can, they're all kind of the same. As long as you draw a picture and get a good visualization, it helps, how many degrees of freedom? 15, sorry. 2.95. Compared to the z-crit for 99, which is 2.58. Again, bigger, but not as drastic. What about 95 for 20 degrees of freedom? No. Be careful here now. For a sample size of 20, degrees of freedom is your sample size minus 1. So this would be 19 degrees of freedom. Be careful there. So this is a t-curve with 19 degrees of freedom, 0.95. 19 degrees of freedom, that's pretty close. It's probably going to be pretty close to the 1.96, but it's definitely going to be bigger. Got 0.25 on each tail. This would be 19 degrees of freedom, 2.093. T-crit, 19, 2.093. Again, bigger than the 1.96, but not as big because your sample size is 20. And your degrees of freedom. Let's go 190 degrees of freedom, 199 degrees of freedom. This is probably going to be really close to the 1.96, 1.97. So even at 190, even a sample size of 200, it's still a little bit bigger than the 1.96 that we get with the z-curve. So that's how you do t-distributions. All right, so this is a good place to stop this video. Now we're going to get into the assumptions and conditions and actually calculating some of these intervals.